Welcome. This is the ITV Technology Forum. This year, the monthly opportunity for you to get in front of your peers in technology and share all the cool stuff we work on. This week we have Lee Coomber who's going to be talking about kind of messaging with Rabbit. I hope everyone got a donut. They were there on the way in. And Lee, over to you. Thank you.
Cool, thank you. So you can see the title of the presentation kind of gives it away. I'll talk a bit about messaging. It's probably the longest section, a bit abstract what you'd use messaging for, what it can help with, what it can't do. We'll talk about AMQP, which is a protocol used in messaging. And we'll talk about RabbitMQ, which is a particular broker we use which implements AMQP. That would be the shortest section because our platform engineers can help you with that. They know the ins and outs. And I'll talk very briefly about alternatives. This is quite a dense talk. I'll make the slides available. There's detailed speaker notes in if you want to follow up on anything. And please ask any questions. I'll also say my knowledge in this area is a bit dated now. It's been a while since I've worked with these things. So we'll kick off with messaging. At its most abstract, messages are a fundamental unit of communication. So it's something that carries information between two parties. So at this abstract level, you're all familiar with the type of messaging, HTTP. So you have a client, makes a HTTP request to a web server, and that request is a message. You get a response back, that's also a message. It should be fairly obvious to everyone what it is. But there's a limitation to this style of messaging. If the server is unavailable, you don't get any responses back. And that just basically kills your client. An unavailable server can be it's gone away, there's a network problem, there's a config issue, or it's overloaded. And if a client generates more work than a server can handle, the server will go away. So it's quite a brittle form of communication. We refer to HTTP as asynchronous messaging or synchronous communication. Synchronous means at the same time. And synchronous messaging is when two parties must be available to communicate at the same time. A web server and client is a good example. So if you need an answer to something right now, like give me this user profile, there isn't really an alternative. You can use caching to reduce the brittleness, high availability, but not all problems are of that form. Quite often we have problems which are something's happened, I need to tell someone about it. The profile for this viewer has changed. The synopsis for tomorrow's episode of Coronation Street has changed. Or store this log entry. These aren't things that have to be handled immediately. So we can look at an alternative. We can put a broker in the middle that basically separates the client and server and will take the messages and deliver them on when it's ready. So if the server is unavailable, the messages will queue up for later delivery. We call this asynchronous messaging. Opposite of synchronous messaging, the systems don't have to be up at the same time. They're independent. So although, technically speaking, things like HTTP are messaging, when we're talking about systems architecture, if we refer to messaging, we're pretty much talking about asynchronous messaging using a broker. That's probably the defining characteristics. There are brokerless frameworks for messaging, but that's a talk for another day. Another important concept here is coupling. So the coupling is an extent to which component depends on another. Those of you devs using OO, you'll be familiar with it from your designs. It applies at an architectural level. It applies at a team level as well. We say that two components that are decoupled asynchronously are decoupled with respect to time. They can also be decoupled with respect to space, which might be an odd concept, but basically if you think about a client and a web server, the client has to know where the web server is, what it does, what it expects back. It's got quite deep knowledge of what's going on there. But with our asynchronous messaging, we could actually just send the messages on to many other people. The publisher doesn't have to know what's going on. So we've seen that you get some resilience from not being services being available at the same time, but also by them not knowing about what's going on means that you can evolve the systems independently. So if we've got a client, broker, and server, You can send the messages to multiple servers. You can even take the messages from multiple clients. So if you have lots of things doing the same thing, you can use a broker to bring them together. I'm going to change the terminology at this point because we're not really talking about client-server computing anymore. We talk about producers or publishers, something that sends a message to the broker. And we talk about consumers, something that receives these messages. So we'll go through an example. It's a semi-real example from ITV because we haven't built some of it yet, and I've amended some of the details to make it easier to explain. So I can see an architect over there who worked on this, so it's not quite what we're going to do. It's an example. So we've got a ITV viewer, and we have a profile service that they use to manage their profile on the ITV hub, and we've got a message broker. So when the viewer registers with profile service, the profile service can announce that fact to the rest of the world via a broker. So it publishes an event saying, we have a new user, Fred, or whomever. That broker sends on the message to a welcome emailer component, which receives that event and goes, we have a new viewer, we'll send them the welcome email. We have another component which sends it onto our CRM system, our customer relationship management system, which means we can send marketing material to them. And we also send it to our system that does ad targeting, so we can work out what ads viewers should see on ITV Hub. Now, there's some important points here. I don't know which screen you're looking at, but the profile service doesn't know anything about these other components, completely decoupled from them. We could add another one, we could take one away. It doesn't know. You can change the architecture as you want. Those other services know nothing about the profile service apart from the fact that it can get a new user message. You may add edited users and things like that, but you're carefully controlling what information you expose between the two parties. And from an operational perspective, the three components on the right could disappear off the face of the earth, and we can still register our users with the profile service. It doesn't break anything. And during big events like World Cup football matches, where we have a huge amount of registrations in a short amount of time, we can use the broker to mediate the load onto those other services. So they pull in, the welcome mailer will work as fast as it can, sending emails, but no faster. So it pulls in messages as it's ready without falling over. And digging into that further, we can actually use the broker to load balance. So if we've got a welcome emailer service that starts up, connects, starts receiving its messages, if we're expecting high load, we can fire up some more. And the broker will just distribute the load across those components. It's no config change, it just happens. If one of them crashes, the other ones will pick up the load. We can bring up new ones, tear them down as we want. So it makes for very horizontal, scalable architectures. So I'll go through a couple of high-level patterns. They're fairly obvious, but I'm guessing a lot of you will be familiar with them, but it's good for terminology. So point-to-point messaging, very straightforward, what it says on the tin. We want to get a message from one point to another, from a publisher to a consumer. Slightly more interestingly, pub-sub, publish-subscribe. So we have a single producer, and that is publishing to multiple consumers, which we'll call subscribers, because they subscribe to the messages, and the broker will distribute them through there. Scatter-gather is slightly more advanced. You have a publisher, you have a number of processors, and the broker will distribute these messages to all the processors and then bring them back again, either by the same broker or another one. If any of you are familiar with MapReduce, you can use this to implement MapReduce if you're not using a framework for it already. And also, if you look at the sort of first half of this, it's also pub-sub. So these patterns often apply in aggregate as well. You can compose them together. My favourite, remote procedure call. You can implement that using a broker. You shouldn't. If you see yourself going down this route, step back, ask yourself why. If you want to do this kind of thing, use HTTP, because you're basically coupling your systems back together again. There's no point in using messaging. A quick thing before we finish the section, I want to be clear that message brokers aren't for storing data. I have seen at ITV before that, and a couple of you smiling, that we used it to store log messages. It's a first in, first out queue, and that is a bad data structure for storing things you want to do random access to. So don't store messages in there. Use it for sending messages. Apache Kafka is an exception, but that is a bit of a different class of machine. So yeah, if you need to store data, use a data store. A quick summary of that then. So when we're talking about messaging in an architectural context, we're generally referring to async communication using a broker. This communication allows us to decouple components in time and space. This is great from a evolvable and resilient architecture. And we're talking about sending messages, not storing them. So any questions on general messaging before we move on? No?
What about your broker? Doesn't that become the sort of single point of failure?
I almost had that in as an FAQ. Yes, it does. So, but brokers tend to be, it's a mediator, and you try and get rid of those to have less moving parts in your architecture. Brokers tend to be built to be very available. That comes with trade-offs, and we'll cover some of those with RabbitMQ. But it's generally far easier to make a broker highly available than other parts of your architecture, because that's kind of what it does. You need to pick your trade-offs. Making brokers available is generally very easy. So AMQP, a bit of history as to explain why we have AMQP. If you wanted a message broker at the turn of the century, or I don't know, 16 years ago, you were pretty much shit out of luck, unless you wanted to go with TIBCO for Rendezvous or IBM for MQ series. Now, that's not going to be everyone's first choice. They cost big money, and they basically lock you in. You have your whole architecture is then tied to one vendor, and for some reason they don't make it easy to interoperate with others. There is a piece of open source software called Spread, which I used at the BBC, but it's not something that I saw widely used anywhere else. It didn't have kind of traction. So step forward, AMQP, Advanced Message Queuing Protocol. It's a queuing protocol for messages. It came out of, it's quite advanced, yeah. It came out of a group at JP Morgan Chase. They used messaging a lot. They paid lots of money to the likes of IBM and TIBCO, and they kind of thought, well, if we come up with a protocol, people can start writing other brokers that are interop, and that will start competition. You've got an ecosystem, life will be good. So that was, I think, 2003 or 4 that they published that. It's a transport protocol for the network. Think of it as like an asynchronous version of HTTP. It's a public version standard. We're talking about version 091 here from 2008, which is supported by many brokers, including Rabbit. There is a version 1.0, which is Oasis and ISO blessed, but it's completely different to 091. There was a lot of politics and infighting that it basically changed a lot of things. So depending on your point of view, it made everything simpler and more focused on better interoperability. Or on the other side, it abandoned essential concepts, which meant that broker fragmentation was inevitable. I don't really care. 091 is well supported everywhere, and that's the one that Rabbit supports as a first-class citizen. It does support 1.0 as well. But as far as I know, the interop with all the other brokers has been nothing but PR exercises. There hasn't really been much other than press releases about it from the major vendors. So it's a network protocol. For those of you who are into these things, it's an OSI layer 7 application protocol, sits on top of TCP. You don't need that yet. It's binary encoded, which means it's efficient to send. It's quite compact. It's designed to be easy to put onto the wire and take off, so you can send things through quickly. And you can send arbitrary size messages. It doesn't have to be just small bits. You can send images. Basically, it's just limited by the size of your broker. So, if you want to send gigabyte messages, you can have performance issues, but work that out with your stack. One thing with the network that confuses a lot of people when they first look at Rabbit is is the multiplexing. So if you've got a client and a broker, and a client can be a publisher or consumer, you'll set up long-lived TCP connections between them, but you won't deal with them generally in your apps. You deal with things called channels, which are multiplexed within those TCP connections. And generally, you'll use a channel with a thread in your application, or a logical unit of work if you're not using something that's explicitly threaded. So for example, you'd have a channel that was just dedicated to publishing one type of message or consuming one type of message. And one thing to note is the commands you send are also asynchronous. The whole thing is asynchronous. So if you're asking it to do things, you need to wait for it to say it's done them before moving on. The protocol, as well as what happens on the network, it defines what you do in a broker as well. It has a broker model. You have a publisher, a broker, and a consumer, as we've seen. A publisher publishes a message to an exchange. An exchange is a bit like an old telephone exchange. It routes messages to different endpoints within the broker. For those of you who are younger, telephones used to have wires in. And they used to go through big buildings called exchanges, which would then route your call to another exchange with lots of wires in and possibly others, and eventually to someone on the other end. And it's a very similar concept there. You have a consumer, which consumes from you have a queue, which a consumer can consume from. And it's a queue. If messages aren't consumed, they queue up. And we have bindings that connect exchanges and queues and allows messages to flow between them. And it's the bindings that kind of give you the power and flexibility in AMQP. So how do messages flow around in the broker? So each message carries a routing key, which is just a text string. Each binding contains a text string, a routing key. And depending on the type of exchange and the routing keys, defines how your messages get routed. So the kinds of exchanges we're looking at are a direct exchange, and this is quite simple. You have a binding key, a message key. If they match, your message gets routed to the queue. If they don't, the message gets dropped to the exchange. If you change the one of the keys, the messages will just stop. They won't go anywhere. And you can have multiple queues bound to that exchange. So you can have different binding queues depending on what messages you want to go to what exchange. Topic exchanges are similar, but they allow wildcard matching. So if we say we had something in our product catalog service that told us when things changed in the various parts of the product catalog. So this example, the synopsis for an episode has changed. We can use wildcards to determine how that's routed. And it's a hash to match 0 or more delimited word, or a star to match one such word. So say we want to get everything from the product catalog. We want to put that on our queue for processing. We'd use hash. If we wanted to just get the synopses for episode or program or series, then we can use the star there and they would flow through. Then we have a fan out exchange. And this is a very, very simple one. The binding keys are just ignored. So if you have a message key of whatever, then it goes to the exchange, and whatever the routing key is on the binding, it will go through to there. Different exchanges have different performance characteristics. You probably don't care because we don't do anything serious enough with messaging to worry about this, but fan out exchanges are incredibly fast because they're not really doing much other than copying messages.
Could you get the same effect by using a direct one and just using a hash as the only thing?
You'd need to use a topic one because, yes, you could.
Same effect, but...
Same effect, but you're having to then process that match each time, which will slow things down. I can't see it ever mattering for most of our traffic. Log distribution maybe gets big enough that you care, but finally, AMQP defines a magic exchange, the default exchange. If you have a routing key of foo in the message and you send it to the default exchange, which has no name, that will basically just send it to a queue with the name of the routing key of the message. And you don't have to create the bindings or any more exchanges, it will just pass it on. don't use this. You'll see it in lots of examples and tutorials. It works, but it kind of hides what your intent is, and you just end up with loads of things being overloaded through one area, and you can't then separate traffic. But if you see this in a tutorial or something, that's what it's doing. You can implement the message patterns we saw in the first part. Pub/sub, you just have multiple queues bound to your exchange, and you use your binding keys and your type of exchange to work out how to, how you want to distribute your messages. All your subscribers may want different things, and you can do that using the binding keys. So, how do you create these topologies? Most brokers allow you to have config centrally. You can kind of say in your config when it starts up, off you go. But AMQP allowed you to do this at the protocol level, which means applications can own their communication logic. So what you can have is your publisher declaring the exchange. So it says, I'm publishing messages of this type, and I'm going to create an exchange in the broker with these parameters, and I'll own that, and it will be created when I start. And all these things are declarative, so if it already exists, life will carry on and it will be good. If the configuration is different, someone's changed it, or it's not what the application's expecting, it will fail hard, which is probably what you want, because normally the things that change are reliability parameters. And consumers create their queues and bindings. So you can see you've got a partition, a clean divide in ownership. Publishers decide where they're publishing. Consumers can basically work out, they manage their own queues, they manage their own reliability features, and they work out what messages they get from the various exchanges. And this is another form of loose coupling. You're not kind of coupled to some central configuration. Consumers and publishers don't need to know each other than the format of messages in the exchange name.
Say I've got a consumer that I've attached to it, so it'll create its own queue, and for some reason that consumer failed, and all the messages that were in that queue, that consumer sort of slid out, waiting for that consumer's just disappeared. How does broker tidy up that queue and put it back into the system?
So it depends on the settings of the queue. You can do it, so what's called an exclusive queue. When the consumer goes away, the queue dies, because sometimes if there's no queue, you don't want the messages, just throw it all away. You can also set it up, and we'll come on to reliability next. If that consumer goes away, I want everything to exist so another consumer can go in. But often you'll have multiple consumers, so they'll share that anyway. So we'll talk about reliability. So it's worth stating that not all messaging use cases require reliable delivery. I think a lot of the ones we have do, but in the bigger world, there's a lot of cases where you don't. You just want to get data from one point to another really quickly. For example, FX trading, currencies. You may have a stream of prices, they change very quickly. If you don't get a price through, there's no point waiting for it to be redelivered. It's invalid, you wait for the next price. So most brokers, you start off with them configured for speed, you add reliability later, because reliability features normally take time and processing to do. Assuming you do want reliable messaging, which we often do, you start off at the publisher level, you need to enable transactions. Transactions basically allow your publisher to be told by the broker, yes, I have taken responsibility for this message. And that is important. In general, with messaging, you want to make sure that there's a responsibility handoff all the way through the chain. The same way as you would with an app and databases and things. You need to know that a component's taken responsibility before you move on. At the queue level, you enable durability. By default, queues aren't durable. If the consumer goes away, actually, that's a different thing. If the broker goes away, when it comes back, the queue will not come back. You'll need to wait for the consumer to come back and declare it, by which time you've lost the messages. So you need to say that the queue is durable. And associated with that, you need to make sure your messages are marked as persistent. This is basically, again, shows the split of responsibility. Publishers can indicate what important messages are and which ones you may want to store to disk and have reliable delivery of. The consumer can then actually say, well, for me it's just an FYI, I'm not going to have a durable queue, so they won't get persisted. But if you want reliability, you need to do both. As a consumer, you should use acknowledgements. So when you've got a message and processed it, you go back to the broker, and it's called acking the message. You acknowledge that you've got it, and the broker will then stop trying to deliver it to anyone. Likewise, you can reject a message. You can say, well, actually, this message is just junk, delete it, or this message is fine, but not for me. I don't want it, I'm going to reject it, but can you queue it up and deliver it to someone else? You can set consumers to auto-act messages, which is very fast. It gets you no reliability. The broker assumes that once you've read it off the wire, you're done. It can get rid of it. And finally, enable durability for exchanges. Again, so the exchange comes back when you restart the broker. This isn't essential. Life will continue if you don't do this, because no messages are stored in the exchange. But what will happen is, if you lose the broker and it comes back, you won't have an exchange to bind to until the publisher comes back up and creates it. The consumer will be trying to, if the consumer's up first, it will be trying to create the queue and bind it to that exchange, and you're just going to have a bit of time while the two try and get their shit sorted. If you just make it durable, it all comes back nice and quickly. AMQP offers some guarantees, which is very important to understand. For ordering, any message going through one channel, through one exchange, one queue, one outgoing channel, will stay in the same order. Never rely on that, because that is such a noddy use case that it just won't happen. If you have multiple consumers, that doesn't happen. If you have multiple publishers, that doesn't happen. If one of your consumers fail and you get another taking up the load, that won't happen. So if message ordering is important, then handle it in your app. Put sequence numbers in your messages, or timestamp, or something like that. Do not rely on the guarantees of a message broker, or any message broker. Some of them do allow you to do this strictly. Think about whether you really want that in those ones, because generally what that means is you're waiting for missing messages to come through. If you think of TCP, you cannot carry on processing until all the packets have been delivered, and if they're missing, you wait for them to be retransmitted, which with messaging generally you get on with it and then try and catch up with missing messages later. And the other interesting guarantee is delivery. AMQP will say that, assuming you follow the reliability guarantees, we will deliver this message at least once. Which may be counterintuitive. People might go, well, I just want my message once. Very few distributed systems can guarantee that for you without putting massive blocks in, or at the cost of availability, for a similar reason. Or actually, if we take a use case, if I have a consumer that's failed without hacking a message back to the broker's got no way of knowing whether the consumer actually processed it or not. So it will have to wait until whatever happened to that consumer is fixed before it can decide, do I need to redeliver this to someone else, or do I know that it's been delivered and carry on? So if you want any kind of availability and life to continue in the event of a crash, you have to accept the fact that sometimes messages will be delivered twice. And again, you need to code for this in your app. But basically what you do is you make your messages idempotent, which means that replaying the same message has no effect after the first time. For those of you into REST and things, it's like put or something like that. And it's for the same reason. It's really, however many times you put with the same request, it will only take effect once, and it is for the same reason. For distributed systems, idempotency means that you can relax consistency guarantees to get availability. Or another approach, which effectively ends up being the same way at the point you process it, is that you put a unique ID on your messages and then dedupe them at your consumer. If you're doing that, I would probably say use a sequence number, because it's easy to hold the state. There you go. So for AMQP, it's a network protocol. You can use exchanges, queues, bindings to implement different messaging patterns, make your messages idempotent. And are there any questions at that point?
So, I'm a broker. Got a feeling like, because you are having not multiplexing happening within the broker, it's not becoming like a very processor sensitive or heavyweight component as compared to the traditional AMQ or something in the
As in CPU intensive? Not really, because essentially what it's doing is copying messages. It's copying data in memory and on disk. And it depends on the implementation of the broker. That's essentially what every message queue, including MQ, rendezvous, spread, and all that do. It's essentially copying bits.
But then opening too many TCP connections, because that's what was, if I understood it right, it'll open a lot of TCP connections.
No, it opens up channels within TCP connections, so you have fewer TCP connections and multiplex within them. In reality, I think that the multiplexing is probably overkill. If you have that many TCP connections, then there's various techniques you can use to load balance. Do that rather than adding a whole concept of multiplexing within a protocol. There's other ways of doing that, which makes the protocol simpler. But yeah, you can use channels, which means that you've used fewer TCP connections. So moving on to RabbitMQ. RabbitMQ is a message broker, implements AMQP. It's written in Erlang, which is a language that come out of telcos. It runs on pretty much any platform. I think ZOS is pretty much the only known exception, which I dare say, no, I was about to say we definitely don't run that here.
Maybe somewhere.
Yeah. There's distributions for most platforms. We've got Puppet modules for it, and most importantly, it's common platform approved. There are clients for pretty much anything in terms of what we use around ITV, Scala, Java, Node.js, .NET, Ruby, PHP Go, all sorted. Several of those have multiple clients. There's also clients for just about every other important language over the last 10 years. No, I haven't. Even Perl. And yeah, you can use it. You can configure it using files, REST API, and a GUI. As I said, though, let applications control the MQP model itself. That's a link to our common platform Puppet template for it. There's a REST API, and there's a web UI. That's an example just from the site. Useful for seeing what's going on and introspecting to there. RabbitMQ gives you a few things over AMQP, and the first and most important is probably clustering, because that affects the interpretation of some of the AMQP guarantees. So you can cluster RabbitMQ nodes together, and we do that in a lot of places, I think in ITV, basically put one in each AWS AZ, and we do this for availability. You can also do it for load balancing, but as I said, I don't think we've got any real need to do that. But basically, having them clustered in different AZs, if an AZ goes down, you can still carry on sending and receiving messages.
Sorry, does it means like physically having a copy of the queue over the clusters?
I'll come on to that in a sec.
In the old world, it was always having another active MQ instance. I mean, I've never seen queue instances or queue brokers getting clustered.
You can configure it. So by default, everything in a Rabbit instance is mirrored to the other instances in the cluster, apart from queues.
That's what I'd
Yeah.
like to know.
Queues, quite often you want data locality. You don't want lots of copying around. If possible, you want a message to go straight to a consumer bound to the location of the queue. It's called the master. For availability and reliability messaging, you can actually choose to mirror those queues across the cluster. And it's up to you. You can do it to certain nodes or a number of nodes. I'd probably recommend, if this is what you're after, do it to all, because generally we don't run nodes for load balancing. You're already running the nodes you want for availability, so just follow that. But there's an important caveat on this, that RabbitMQ does not tolerate network partitions very well. It focuses on availability. For those familiar with Brewer's theorem or CAP theorem, it's consistency and availability, not network partitions. It's possible to get into a point where if you have a certain sequence of partitions and publishers going to publishing to multiple Rabbit instances, that you get what's called a split brain, where one side of a cluster doesn't know what's happening on the other side. And then when the partition is resolved, they can't actually resolve and get back to what's going on. And at this point with Rabbit, you will lose messages. There's no way of doing anything else. Rabbit will tell you that there's been a problem. There's various log messages and events you can trap for, but that can happen. You can use a thing called pause minority mode, which helps prevent it. You basically, if a cluster detects it's in a minority, it will stop receiving messages to try and avoid this problem, but it can happen. It is rare, but it's something you need to think about. Has anyone actually ever seen it here with Rabbit? Yeah, it can happen. So there's another orchestration thing that Rabbit gives you called federation. Now this is where you join two clusters logically together. Two nodes logically together without clustering them. So you have more control about what's going on. So you can federate exchanges, and that's where two exchanges are bound together. So any message sent to the exchange in broker A will be routed to the one in broker B. There's also federated queues. Now this isn't queue mirroring, this is upstream, downstream. It's a message flow through queues. And you can use this for load balancing. We don't use it here as far as I'm aware. But basically, once the queue in downstream, so in this case broker B is empty, it will pull in more messages from the queue in broker A. So if you have lots of downstream brokers, or downstream queues, you're spreading the load. Federated exchanges are far more useful for what we do, and we do use them in a few places. Content delivery, and yes, there's people from there. We use it there because we have two brokers, one internal, one that's open to the outside world, which Deluxe, our content processor, uses to send and receive messages. And we use federation to connect the two, so we're not basically putting our internal broker out on the internet. We also use it online for our user registration team. There's a legacy stack that uses Rabbit, and we have a new stack that uses Rabbit, and we keep the two separately, and we federate between them so that we join up the older services from the newer services, but still maintaining separation for operations.
A question on design patterns then. In terms of, it's likely there are two different systems, independent systems. Is it another pattern you could have a worker to consume a queue on this side, and actually it knows that it needs to take a HTTP post or put to a remote system, and in their response they'll actually do a post or put back to you. So actually you move the messaging to HTTP between two very disparate systems, but they're still kind of consuming from a queue behind the scenes, but actually you kind of keep a black box. I've seen this pattern before, and I think it works. It feels like it's coupling at a layer kind of below what we guys kind of like to.
So are you kind of saying, is there a way for federation or messaging in general?
Well, it's kind of as a design pattern where you often can solve it with this federated approach where you need to exchange messages between two separate systems. But I was wondering kind of from a pattern perspective whether you could also have a worker that's listening on client A listening to that queue, and it knows
yes.
I need to post to my remote end and then post back. That is also
you can do, and in fact I think Rabbit has like a plugin for basically taking messages and sending them to a webhook somewhere, for example, and sending messages back.
Yeah, this feels, I've always kind of felt like queues are kind of an internal, kind of under the hood thing, and like linking two separate systems with them.
It would come down to what you thought HTTP gave you over this, because almost anything you're doing HTTP you could do using AMQP. Like schema validation doesn't come with either protocol, you'd have to do that on top, and various validations and things. This isn't, in terms like the user registration use case, you wouldn't build a service just to link those two systems. It's a handy integration layer. With the one with Deluxe, maybe we would. I think at the time it was seen as an easy way forward, but maybe that would be a cleaner separation. The more interesting thing with federated exchanges is you can use it for reliability, because it is very partition tolerant.
Throttling? Just to throttle? I don't know if it's a valid scenario to use it.
No.
Not for that. So
No.
I want to funnel out and I say like, okay, there are 2,000 messages stacking in broker AQ, and I start to sort of like implement, let's say there's 500 I want to get into my second queue. Use it as a throttling point.
You can use it to distribute load. So you could, for example, use the federated queues to basically distribute the messages being sent across multiple brokers. So you could, if you had a load, you could do it that way, but that's very pull-based, which generally with messaging, it's kind of event-based, it's pull-reactive type pattern going back. Rabbit does offer some, like a sharding exchange and things like that, if you wanted to do it like that. Otherwise, you'd need to work out how you were doing that split. And throttling would more come down to what you do with the publisher, and I'll mention it very briefly at the end, but it gets quite, it's more detailed than I'll go to here, but I'll refer to it at the end. But yeah, the interesting thing about federation is, reliability. So whereas clustering isn't partition tolerant, federation is, or federating exchanges is. So under the hood, it basically, you can probably see this from most, there's actually a queue in here. You don't manage it, the broker manages it. If the link between broker A and broker B goes down, then when it's re-established, all the messages will be re-delivered. You don't have any loss. But that comes at the expense of consistency. You have to trade off somewhere. So basically, all messages go. You can't control whether you've seen them or not. So I'll go through a little example. If you had two brokers, a publisher publishing to an exchange that was federated to another broker, you could basically replicate the topology on both brokers. If one went down, the publisher can just switch to the other one. You're not going to lose any messages. Any messages that were, if you got unlucky and one was being processed right at that time, when broker A come back up, it would get redelivered, albeit later. So that would be a very reliable way of delivering messages. It comes at the expense to the consumer. It has to deduplicate the messages there. Now, you should be doing that anyway, but there's normally a difference between dealing with the odd duplicated message and dealing with all duplicated messages. For example, I know one use case with content delivery. If there was one type of message that was duplicated, it would mean that an order went to deluxe, which had a financial cost. But the financial cost was small, and it was thought, we'll take the financial cost of that occasionally happening rather than try and deduplicate, because it's not a big deal if we do have duplicate messages. But if you're having to deduplicate all, then you have to pay a lot more attention. Yeah, so that's it failing over. A couple of other features that you should know about. Transactions in AMQP are very slow. RabbitMQ has their own kind of version of a transaction for publishers called confirms, which are fully async and can take batches as well. On the converse side, they've introduced a thing called NAC messages. They've extended the protocol, which is much faster than rejecting messages because you can do them in bulk. A few odds and sods. It's sometimes useful to temporarily reject a message if you can't handle it at the moment. We have cases in online where we'll be told something has changed. We want to refresh the record that change refers to. We can't get to a back-end system. We don't want to drop the message. We do want to do it. We just want to retry later. So we use some internal, a bit of a mess, but we can do it internally to do that using AMQP. If you want to know more about that, ask me or Kilter or Dave. I think you've probably had to use it. There is a plugin that does that now in Rabbit. I haven't used it, but it's worth looking at. Temporarily rejecting NACing messages. Platform engineers will be able to help you with monitoring the broker, but app developers should really worry about queue length. If the queue starts getting too long, it means something's gone wrong in your system. But what too long is down to what your application is. You might expect it to get very long at times because you have very up and down traffic. Other ones, you'd expect messages to be consumed almost instantly. But that's something to keep an eye on in terms of health. And kind of addressing your question, Vinay, if you want to throttle, you really want to do it at the publishing end. And there's a couple of ways of doing back pressure. There's pure TCP back pressure, which the broker understands. And we'll use TCP mechanisms to make a publisher back off. It's also in the protocol as well. RabbitMQ extends AMQP and basically allows the broker to tell a publisher that I'm blocking you for a while. Yeah. And that's based on you need to look at the docs, but basically it's based on how much memory and I think is being used in the broker. I think there's a credit mechanism based on consumers. So if a publisher's not getting enough credit back from consumers in the topology, then it will apply back pressure. ITV interesting projects. We have an AMQP Client Library for Scala in Hub Services, which is used in a few places. There's a link to it now. It's a bit dated. And content delivery are going to open source, I'm assured, very soon. Bucky, which is a newer one. On that note, you too can an open source work. There's a guide to how to do it online. If there's anything you're working on that you think is of value to other people, and you want to share it, then have a look there. We have now mechanisms for doing that. We have an ITV open source license. And yeah, you can talk to me or other people about going through that. This is going to be very brief because I haven't really looked at many other alternatives in Anger. What are the alternatives to RabbitMQ? There are no alternatives. So if I was in the market for an alternative, I would probably start off looking at AWS SQS. It's a simpler model. I think it's just queues. It's one of the few brokers that is clear that you don't suffer message loss under split brain, but they really relax the ordering guarantees, and you're more likely to get duplicate deliveries to achieve that. But that's the way you have to do it. Historically, it's had latency issues. I think that's gone. I think you get messages through in a few hundred milliseconds end to end. It requires HTTP polling, which is untidy, but I think probably works. There's vendor lock-in. You're locked into SQS. There's no open source equivalent. But if you use appropriate abstractions in your code, then it shouldn't be too worrying. Messaging is a very simple thing. It should be easy to swap out how you do it in your code. I'd also have a look at Apache Kafka, which is more of a distributed transaction log. You can use it for messaging, but it will also store those messages in order for you. So that's kind of interesting because it would probably change the way we wrote some applications as well. You can make them far more event-based because your apps can basically catch up on history because Kafka will very efficiently deliver it again for you. And the third thing I'd look at is ZeroMQ. This is a brokerless framework for messaging, async messaging. Basically gives you lots of building blocks for building different messaging patterns, and lets you kind of do little funky network clusters and stuff that give you a load of reliability guarantees. And it's also written by, or the main person behind it, a guy called Peter Hitchens, whose blog is definitely worth reading. He writes fantastic stuff about protocols, messaging, an open source culture and things like that as well. He's written a great attack on what went wrong with the AMQP specification and the process rather than the protocol itself. There's a bit of further reading. Enterprise integration patterns kind of talks around enterprise integration patterns, but it covers a lot of messaging concepts and things in there as well. AMQP has a load of stuff on that. If you want to learn about RabbitMQ, the docs are excellent, and there's a lot of tutorials and stuff around it, and that's a good place to dig into AMQP if you want the details as well. Yeah, we don't need spares. Any questions?
Just on the alternative side of things, MSQ, is that right in the list at all?
Which one?
MSQ?
I don't know it, I'm afraid.
That's the one from Bitly?
No, don't know it, I'm afraid. But I said I'm not an expert on the wider ecosystem, so.
And the other one was from the application point of view, didn't touch on the DNX concept for Rabbit as well, dead letter exchange.
Okay, that's true. So you can, it's an important point actually, thank you. If a message can't be delivered for whatever reason, it's rejected or it times out, if you set that on it, you can set a queue to have a dead letter exchange where all your messages that can't be delivered are sent, which means you can have a manual automated process to pick those off and deal with exceptions without blocking your main message flow. But yeah, that's an important point.
You don't use JMS anywhere?
No, JMS is an API specification. It's not a protocol. in itself. It specifies an API.
Yeah.
So all the implementations are not interoperable, other than at the API level. So if you're using ActiveMQ, you have to use the ActiveMQ library because the actual wire protocol is different to say, well, actually, RabbitMQ I think has a JMS plugin. They won't interop. The interesting thing about AMQP was the fact that it made brokers interoperable, or that was a theory.
Yeah.
What's the difference between Stomp and AMQP, and why would you use it?
I'm not an expert on Stomp. It's a much simpler protocol. It doesn't give you all the same topology models, but it may give you enough. I think Play Browser used to use it to actually talk to RabbitMQ because there's a Stomp plugin.
Use Stomp for inflected, AMQP for sensitive compound.
Yeah, I don't know enough about it. It's a simpler text-based protocol, which I think, if your use case is simple, is probably fine. There's also MQTT, which is, again, if you've got, it's designed for Internet of Things, kind of small consumer devices, very lightweight protocol, which again, I think if your use case is simple, probably gives you everything you need. Cool, thank you.